All right, welcome to Chapter 1, Lesson 6. Today we're going to be talking about solving compound and absolute value inequalities. This is going to build off what we covered in Lesson 4 and Lesson 5. So, what we're going to learn in the lesson today is how do you solve compound inequalities and how you solve absolute value inequalities. So, you've worked with inequalities in Lesson 4, and you've worked on absolute value equations, I believe, in lesson 5. So some vocabulary to keep track of is what is a compound inequality, an intersection, and a union. So here's an example of how we can use compound inequality in medicine. So it says one test is determined whether a patient is diabetic and requires insulin is a glucose tolerance test. Patients start the test in a fasting state, meaning that they have no food or drink except for water at least 10, but no more than 16 hours. The acceptable number of hours H for fasting can be described by the following compound inequality. So it says that it has to be at least 10 hours of fasting, but no more than 16 hours. So basically, we're giving a data set that's got to fit between those two values. So a compound inequality that could represent that would be that H, the number of hours, has to be greater than or equal to 10. And those hours H also have to be less than or equal to 16. It has to fulfill those two requirements. So this is an example of what a compound inequality would look like. So compound inequalities, here's our first vocabulary term. It consists of two inequalities joined by the word and or the word or. To solve the compound inequality, you must solve each part of the inequality. And the graph of the compound inequality containing and is an intersection of the solution sets for those two inequalities. So let's look at what that means. So a compound inequality containing the word and is true if and only if both inequalities are true. So for example, if I had an inequality that said that x is greater than or equal to -1, here is the solution set for that inequality. And if I had another inequality that said x had to be less than 2, right, which would be this solution set here, the compound inequality for that would be if x had to be greater than or equal to -1 and less than or equal to 2, the solution set is the intersection of both of those solution sets, right? So our solution set to this compound inequality would be this intersection right here, right? These would be all the values that are greater than or equal to -1 and less than 2, right? This is the solution set for that compound inequality. Another way of stating this is you can write them separately as x is greater than or equal to -1 and x is less than 2, or you can write them jointly like this, still having two inequalities, but you have the variable in the middle and the two values on the outside. Both forms are read the same way. One little study tip here is interval notation. So this compound inequality here can also be written in interval notation where we use the this type of notation here. Again, you have the lower extremity and the upper extremity, right? So you have the lower value -1, the upper value 2, parentheses meaning that it cannot equal 2, but up to 2, right? And this one right here would be in that it does include -1, right? The bracket. So brackets meaning it includes that value. Parentheses means it does not include that value. It's up to that value. Okay. All right, so let's look at an example. How do you solve an and compound inequality, right? A compound inequality with the word and. So here's the problem. Solve 13 is less than 2x plus 7, which is less than or equal to 17, and then graph the solution set on a number line. So I'm going to show you two methods. The first method is write the compound inequality using the word and then solve each one. So we can write them as two separate inequalities. We can write it as this one, and then we can write it as this one. So here are my two inequalities. So basically I took that inequality and wrote it as two separate inequalities, right? 13 is less than 2x plus 7, and 2x plus 7 is less than or equal to 17. So I can go now and just solve each one separately. So I'm going to solve this one. I would go ahead and subtract 7 from each side, and I get 16 is less than 2x. Divide both sides by 2, and I get 3 is less than x, or x is greater than 3, however you want to read it. I'm going to solve the other one, subtract 7 on both sides, divide both sides by 2. I get x is less than or equal to 5. The second method would be to solve them together. And if you just write it at the same time, you will, if you noticed, I did the same steps on either one, subtract both sides by 7, divide both sides by 2. So when we solve them together, you will notice that you have, essentially a left, a middle, and a right. And basically you would subtract 7 from all of them, right? I think my video here is getting in the way. You would subtract 7 from both of them, divide both by 2, or all of them by 2, the left, the middle, and the right side. And you would be left with the same inequality here. And again, most likely you would see the inequality written this way. This is kind of the most common way of writing it, right? So my x value is going to be greater than 3 and less than or equal to 5. So now we have to graph this solution set for this problem. So if I'm going to graph the solution set, I got to find the intersection of these two inequalities. So x is greater than 3. Obviously, this is the graph of that solution set, right? For all values of x that are greater than 3, not including 3, cannot equal 3. And then the solution set for x is less than or equal to 5 would be everything including 5 and less than that. Now, my solution to this compound inequality is going to be the intersection of these two graphs. So this would be the solution set for my problem. Because it's a compound inequality, it is the intersection of those two. So it would be all the values that are less than 5 and greater than 3, right? So any value that's greater than 3 and less than or equal to 5. Okay, so my solution set does include 5, but does not include 3, and it includes everything in between. So the graph of a compound inequality containing or, so now we've talked about the and, let's talk about compound inequalities that have or, is the union of the solution sets of the two inequalities. So our and statements was the intersection, our or statements is the union. So or compound inequalities is when a compound inequality containing the word or is true if one or more of the inequalities is true. So this one, it doesn't have to fulfill both requirements. It only has to fulfill one of them. So for example, if I had x is less than or equal to 1, here's what it looks like. Here it says x is greater than 4. This is what it looks like, right? And so my compound inequality would be the union of those two. So basically, I get to include both of those because my solution can be one or the other. It just has to fulfill one of them in order to be part of the solution set, right? So x can be either less than or equal to 1, or it can be greater than but not equal to 4. Okay, so basically all of the values to the right of 4, not including 4, and all of the values that are less than, including 1. Okay, so let's practice solving an or compound inequality. So it says solve y minus 2 is greater than negative 3, or y plus 4 is less than or equal to negative 3, and graph its solution set. So it's not saying you can graph one or the other. And it's not asking you to solve one or the other. This is an or compound inequality. It's basically stating that our y values will have to fulfill this inequality or this one, right? It can fulfill either one of them. So I'm going to solve each one separately since it's written separately. So I have y minus 2 is greater than negative 3. So for this one, I would add 2 to both sides, and I get y is greater than negative 1. On this one, I would subtract 4 from both sides, and I get y is less than or equal to negative 7. So I have my two inequalities. So I'm going to go ahead and graph the first one. So this would be the graph for y is greater than negative 1, not including 1. This is my graph for y is less than or equal to negative 7. Again, it includes 7 and anything less than 7. So y can be either one of these. So again, my solution set is the union of these two solution sets. So my compound inequality will have both of these because y can either be any value here or here. Okay. So the solution set, and this is just a very formal way of writing it, the solution set is that for all values of y, y will be greater than -1 or less than or equal to -7. That's how you would read that. So just another quick studies tip. Again, interval notation, right, is the union of these two. So if y has to be greater than -1 or y has to be less than or equal to -7, this would be the interval notation for that, right? So y would be all the values that are less than -7, including, that's why that bracket is there, all the way to -infinity. Since -infinity is not a value, it can't ever include it. It just heads off in that direction. And then it also is the union. That's what the little u is there. From -1, not including -1. That's why the parentheses there, all the way to positive infinity. So both directions of that. So again, this is written as an inequality, and this is written in interval notation. So absolute value inequalities that we learned about in lesson 4 talked about how the absolute value is now the distance that a value is from 0. So, if we're looking at absolute value inequalities, we're going to be looking at the same thing as the distance from 0. So make sure to keep that in mind when we're working with absolute value inequalities. So it says solve the absolute value of a less than 4, graph the solution set on a number line. So remember, the absolute value of a means that no matter what value a is, its distance from 0 has to be less than 4, right? So remember, distance from 0 means that it could be positive or negative, because distance we really measure as a positive value. So we know that whatever value a is will have to be less than 4 units from 0. So what that looks like is, well, here's 0. Anything here, right, less than 4 will be less than 4 units away from 0. But also on the negative side, anything greater than -4, right, all the numbers in this direction are greater, will be less than 4 units from 0, right? So all of these values in between here would fulfill that requirement of the distance being less than, the distance from 0 being less than 4, okay? So again, if you notice, the graph also would match that compound inequality, that a is greater than -4 and less than +4. And so when we go through and solve these absolute value inequalities, we're going to use that to our benefit. And again, this is just a formal way of writing, saying the solution set is for all values of a will be greater than -4 and less than 4. So let's look at this example. So now they want us to graph an absolute value of a that is greater than 4. So again, whatever value a has, its distance from 0 has to be greater than 4. So again, if we look at that solution set on a number line, it's much easier to see. So here's my number line that represents all the values of a, the absolute value of a, where it's the distance from 0 is going to be greater than 4, right? So any value greater than 4 will have an absolute value greater than 4. And any value that is less than 4 or -4 will also have an absolute value that is greater than 4, right? These will all have distances greater than 4 from 0. So again, notice that now it shows the or of that or compound inequality, where values of a are greater than 4 and values of a are also less than -4, right? It is the union of those two inequalities. Okay. So an absolute value inequality can be solved by writing it as a compound inequality, as you were noticing that those two absolute value inequalities that we just went over could be written as compound inequalities, right? Depending on which direction the inequality was going. So if you have an absolute value inequality that's less than a value, it can be written as an and statement. On the flip side of that, if you have an absolute value that is greater than a certain value, then it can be written as an or statement, right? So that's kind of a way that we can look and start to solve absolute value inequalities. So for example, if I had the absolute value of 2x plus 1 is less than 5, then I could write it as an and statement. I could say that 2x plus 1 would have to be greater than negative 5 and less than positive 5. If I looked at the same problem, but the inequality was flipped, if it was the absolute value of 2x plus 1 has to be greater than 5, then that could be written as an or statement, where 2x plus 1 has to be greater than 5, or 2x plus 1 has to be less than negative 5. Okay. These statements are also true whether it's less than or equal to or greater than or equal to. It still holds true. So one other thing to think about is if you ever have an absolute value that is less than a negative number, that is an empty set, because you will never find any value that when you have the absolute value, right, distance from 0 is going to be less than a negative number, right? You're never going to find a distance being negative. So that's always going to be an empty set whenever you come across an inequality that has to be that's an absolute value less than a negative number. It just will always be an empty set. There is no value that will work for that. And then on the flip side of that, if your absolute value is going to be greater than a negative number, right, then that will mean that it always works. Any value that you put in for A would be part of the solution set. So your solution set would be all real numbers. So these are just two instances where when your absolute value is the inequality is compared to a negative value, those are two instances where it's either going to be no solution, right, an empty set, or it's going to be all numbers because it's always going to work no matter what the value of A is. All right, so let's solve a multi-step inequality here involving an absolute value. So the absolute value of 3x minus 2 is greater than or equal to 6. So again, since my absolute value has to be greater than positive 6, right? So it's going to be one of those or statements, right? Because that value has to be greater, right? Its distance from 0 has to be more than 6. So it's going to be that positive side and that negative side. So I'm going to write it as two inequalities. All right, so I have 3x minus 12 is going to be greater than or equal to 6, or 3x minus 2 is going to be less than or equal to negative 6. So again, if you notice, what's inside of the absolute value is going to be greater than or equal to 6, and what's inside the absolute value is going to be less than or equal to negative 6. And so again, I'm going to solve each one. So this one, I add 12 to both sides. I divide both sides by 3, and I get x is greater than or equal to 6. Over here, I add 12 to both sides, divide both sides by 3, and I get x is less than or equal to 2. So here is my solution set for that, right? Here is the x values for this absolute value inequality that will make it true, right? All of these values that are going to be less than or equal to 2 will make this true. They're all part of the solution set. And any value where x is greater than or equal to 6 will also make this inequality true. And you could actually test these values. You can substitute them in for x, and you would always give you a true statement. It would always make the inequality work. So that here's the solution set, right? For all values of x, x must be greater than or equal to 6, or x must be less than or equal to 2. Let's look at another example. So now we're going to write an absolute value inequality. So here's a problem, right? A word problem. So we have to write one out based off the situation. So it says to prepare for a job interview, Megan researches the position's requirements and pay. She discovers that the average starting salary for the position is $38,500, but her actual starting salary could differ from that average by as much as $2,450. So first thing I'm going to do is I'm going to write an absolute value inequality to describe this situation. So first I have to set the variable. So I'm going to let x be the variable, and it's going to represent Megan's starting salary, which can vary, right? Anything within that range there. So her starting salary could differ from the average, right? By as much as $2,450. So here's my absolute value, right? So the average is $38,500 minus x, right? Whatever Megan's starting salary would be, right? And that average, right, or that difference from that average, whether it's above or below, will have to be less than or equal to the $2,450, right? Because that's how much it can vary by. It can be that much above or that much below, right? So if I take the difference from hers And whether that comes out to be positive or negative, right? Really, I'm just making sure that the distance that those two numbers are from each other are going to be less than or equal to that $2,450. So now let's go ahead and solve it, right? So this is the inequality that I wrote here for the problem. And now I'm going to solve it to find out the range of Megan's starting salary. So first I'm going to rewrite this as a compound inequality. So since this value has to be less than or equal to that, right? This distance from 0 is going to be that. It's going to be an and compound inequality. So here's my compound inequality right here. So negative 2,450 has to be less than or equal to, right? The 38,500 minus x, which has to be less than positive 2,450. So this is my compound inequality. So I'm going to go ahead and solve using that second method where I can solve all of it at the same time, right? And so I would subtract 38,500 from all three sides there. And then that would leave me with negative x being greater than or equal to negative 40,950 and less than or equal to negative 36,050. But again, I don't want to solve for negative x. I want to know what x is, right? Positive x. So I would divide everything or multiply everything by -1. But when I do that, right, it changes the sign of everything. But when I do that, it also flips the inequality symbols, right? So this would tell me that x, my value of x, is going to be greater than or equal to 36,050, but less than or equal to 40,950. So there's my solution set right there. And typically you would see it going in the other direction. You usually have the smaller value or the lesser value on the left and the greater value on the right with the variable in the middle. So the solution is set for all values of x. X will be greater than or equal to 36,050 and less than 40,950. So that's Megan's starting salary will range between there. So that was our lesson for solving compound and absolute value inequalities. Thanks for watching.